Hey, welcome back to your favorite pre-calculus class. Today's section 2.5, graphing techniques, transformations. There's our objectives there. Let's start off with an example. We've got the old classic f of x equals x squared. So if you were to graph the old classic y equals x squared, as we've talked about before, it's going through point there, 0, 0. Oops, 0, 0. There's your y equals x squared. Now, if we were to graph g of x equals x squared plus 3, we could just point plot. If you remember, plug in 0 squared plus 3, we get 3. We plug in 1 squared plus 3, 4. 2 squared, 4 plus 3, 7, and so on. We could keep graphing this. Soon enough, when you put these points on, you're going to see the exact same graph, but it's shifted up 3. So this is called a rigid transformation, transformation, which is a vertical shift up 3. So vertical shift up 3. So anytime you have the original function, you put something on the end there, plus or a minus, it's going to shift it up if it's a plus or down if it's a negative. So like right here, you've got a minus 4. So this is just going to shift the x squared function, the parabola, down 4. Okay, you can see a picture of it right there, shifted down 4 units. So there's your generalization of that. If it's a plus k on the end, you're going to go up. If it's a minus k on the end, you're going to go down. K being positive. Now, what if you have something like this here where you have a composition? So instead of just x underneath, if you remember the square root of x looks like that, you have x minus 2. So what you did is you took f of x and you went f of x minus 2. So you plugged x minus 2 in for the original x. Okay, so you see it right there. So if you were to graph that, you plot some points again. You throw 2 in, 2 minus 2, 0, square root of 0, 0, 3 minus 2, 1, square root of 1, 1. And you could keep going with that. 6 minus 2, 4, square root of 4, 2. And soon enough, you graph those points and you're like, oh, it looks exactly the same, except it's been shifted right. So that is a horizontal shift right 2. So it's kind of counterintuitive. You got that minus 2 inside there, but it actually shifts it right 2. Okay, there's a little better picture of that. So again, that's moving it right 2. Whereas if you had a plus underneath there, right there, you're going to be moving that thing left, in this case left 4. So when you have that composition, and there's an example of that, notice it shifted it left 4. There it is. All right. Took the original square root function, moved it left 4. So here's another composition. It took the x squared, it moved it right 3. You see it there in red. It shifted the original function right 3, whereas this one moved it left 2. There's your left 2. It's the quadratic. Okay. So there's the generalization of that. You notice your composition there. That's right h units. This one is left h units. Okay. Alright, so now what if you have you have a vertical and horizontal shift here? Well, this one's the old classic. The parent function here is the absolute value. So here's the absolute value function, original parent graph. So if you notice the minus 5 on the end, that thing's going to go vertically down 5. And that right there is going to move it left 3. Horizontal left 3. So we're going to take it, go down 5 and left 3. And you're going to see that exact same function. There it is. Okay, down 5, left 3. You notice there, first they're shifting it. They're showing you that, hey, we're shifting it to the left, and then we're shifting it down 5. Now, what if we put a constant in front of the original function? If you've got this if you got this number there right, you put it right in front of it, so k root x, in this case it's a 2 root x. If that function is greater than 1, this thing will, let's see if you can see it here. Here's the original, oops, square root function. Now if I was to graph 2 root x, plot a few points, throw in 0, square root of 0, 0, 0 times 2, 0, plug in 1, square root of 1, 1, 1 times that 2 in front, 2, and I keep going with this, square root of 4, 2, 2 times the 2 in front, 4. Soon enough I graph this, and you're going to see this thing be a little steeper. So if that number in front is greater than 1, you will have what's called a vertical stretch. That's by a factor of 2 in this case. Okay, so stretch it out. Whereas if that number, on the other hand, was between 0 and 1, and here's a picture of that, by the way, 2 root x. If that number in front, like this, is between 0 and 1, if that k constant in front is between 0 and 1, what it's going to do to the original function, here's your absolute value of x, what it's going to do is it'll flatten it out. That's called a vertical compression. Vertical shrink or vertical compression. Whatever that number right in front of that function is between 0 and 1. Okay, here's a picture of that. You notice that it's been flattened out right there, hasn't it? Okay, so vertical compression. So there's your generalization. Again, if the number in front is bigger than 1, vertical stretch. If it's between 0 and 1, it's a vertical compression there. Okay, oops. So now that brings us to horizontal compression or stretch, on the other hand, is the other way around. So a horizontal compression results if your a is bigger than 1. Okay, and that's for f of ax. Whereas it'll be a horizontal stretch if your a is less than 1, bigger than 0. So here's a little picture of the two, vertical compared to horizontal. So here's your original function f of x. Notice that the domain goes out here to 3 pi. Notice this point pi halves comma 1 right there. This right here stretched that out. So it took that pi halves 1 and stretched it out. Okay, the domain's still the same. So this was the original. Okay, and it vertically stretched that by a factor of 2. See how it took those points and stretched that by a factor of 2? There's the original. There it is, stretched out. Okay, and that's because of that 2 in front. Whereas right here, see that 3 right there? Now, when the a is greater than 1, this is a horizontal compression, actually, a horizontal compression. Okay, so that original went clear out to the 3 pi. So it compressed those points. Here's the original. Okay, pi halves 1, for instance. Now you got pi 6 1. So that pi halves 1 was compressed in. That point was compressed in. Okay, so everything's been compressed, horizontally compressed in, and that's because of that composition with the constant there in front being greater than 1. Okay. Alright, now reflections. First of all, a reflection about the x-axis. If you put a negative in front of the original function, so here's our x squared, alright? If we were to put a negative in front of that thing, it would reflect that about the, oops, it's supposed to look the same but flipped over, but it reflects it about the x-axis. If you were to plot some points, plug in 0, 0 squared, 0, negative 0, 0. Plug in 1, 1 squared, 1, then you apply that negative in front, and so on. And you plot some points there. You see that thing flipped over. So that's a reflection about the x-axis right there. Reflection about the x-axis. Okay. There's a nicer picture of that. There's the generalization of the reflection about the x-axis. Now if you put a negative inside, so you do a composition here, you do this type of a deal, alright? Put the negative inside, replace the original. Here's the original square root of x function, alright? Now if you put it inside and you start graphing this, let's plot a few points here. Throw in 0, square root of 0, 0. You got to throw in negative 1 because you're taking square root of negative times negative 1, which is 1, then you take the square root, and so on, and you can plot these points. Soon enough you see, here's your reflection about the y-axis now. Okay, so this is a reflection about the y-axis when negative x goes in for x. There's your little nicer picture of that. You notice again the reflection about the y-axis. Right? And there's your generalization. Alright, that brings us to combining some graphing procedures here. If you're looking at this function, hopefully you're thinking about y equals 1 over x as your parent function. So here's your y equals 1 over x. Okay. And so you're going to be manipulating this. If you want to think about this, what are your shifts and all that stuff? And first of all, that's going to go down 1. So that's your vertical down 1. That's what many students consider the easiest one. That's going to move it horizontally. Again, the horizontal one's counterintuitive. It's actually left 2, even though it's a plus 2. And notice the 2 right there. That's going to stretch it out. So you may want to think about this as 2 times 1 over x plus 2, and then minus 1. So there's our vertical stretch. Okay, so stretches it out, moves the left 2, down 1. And that's what you're going to be looking at here. That's just showing you printed form of that. So here's your original. That's showing the vertical stretch. Now you're replacing x with x plus 2, so this is the horizontal shift left 2, and finally the down 1. And here's the pictures of that. There's your original 1 over x. Right there, 1 over x. There's the vertical shift by a factor of 2, so it stretches it out. Notice the point 1, 1 is now at 1, 2, so it's shifted it vertically, stretched that out by a factor of 2. And now it's taken that vertically stretched by a factor of 2 and it's moved it left 2. Alright, notice everything's moving left 2. So that 2, 1 becomes 0, 1. And then finally this thing gets moved down 1. Down 1. So there's the final graph on that. Vertical stretch by factor 2. Left 2, down 1. Thanks for watching. See you guys in class.